In this video, we'll look at section 3.2, one of the main motivations of group theory, which is symmetries. So looking at an object or some sort of structure and look at all the different symmetries that it could possibly have, and then looking at ways you can combine those symmetries together and seeing if it creates a nice structure like a group. So in this one, we'll look at some basic shapes and look at all the possible symmetries it might have. So first we'll look at the rectangle. So you can think of a rectangle as sort of fixed on the plane, but you could also think, what can you do to it? Like if it was a floating object, like imagine this as a floating rectangle, how you could change it or move it around so that it ends up looking the same. Like if you were to blink and something happened and then you look back, it looks exactly the same. So some obvious things, like you could take the center of it and just flip it about the center. So if I were to flip it across that line, then it would look exactly the same. We'll call that operation, that flip, V. You could also do it through a horizontal line through the center. If I flip it about that line, it would also look the same. Now there aren't any other lines I could flip it through because, like if it was a square, I could maybe go through the corners or something like that. But with a rectangle, if I were to flip it through the corners, I would still get the rectangle, but it would be, long ways up and down. The only other thing I can do, besides flipping, is rotating it. I could rotate it around, and I'd have to rotate it a full 180 degrees to get it looking the same. So if you take this point in the center and rotate about that point, every point around here, it would end up looking the same. So I'll call that R. Now another thing we can do is just leave it alone. So if I don't do anything, I'll usually just call that ID for the identity. Now here we want to see how these interact with each other, creating what we call the multiplication or Cayley table for these operations. So we have 4 operations that we'll put in like a multiplication table. So we'll list each operation here and list them all here in the same order. And then see what we would get if we start combining them together. Now, if I combine any operation with the identity, of course I get the same as that operation. So the identity followed by any of these operations just gives you that operation. But now let's think about doing these operations one after another. So in here it's not going to matter, but we'll always take the row as the first operation and the column as the second operation. Again, it's not going to matter in the case of the rectangle, but it will for the equilateral triangle. So if I were to rotate by 180 degrees and then rotate it again, well, what do we mean by the effect of that? Well, let's temporarily label the corners, say A, B, C, and D. When I rotate, this A comes to where C is now, and the B goes to where D is. But if I rotate it again, the A went to C, A is going to come back to where A was again. So in other words, rotating at 180 degrees twice just gives you back to the identity. And actually, that's true for the other operations as well. If I do the vertical flip, A and B and C and D switch places. If I do that vertical flip again, they just switch back. So the vertical flip followed by a vertical flip is the identity, similar with the horizontal flip. Now let's see what happens if I first do the vertical flip and then do the rotation. So let's just track where A goes. So if I do the vertical flip, A goes here. and then the rotation brings it here. So A is now here. What is that similar to? Well, that's similar to if I just did the horizontal flip. A ended up here. So it looks like vertical followed by the rotation is the same as just a horizontal flip. And actually doesn't matter the order. If I do that the other way, let's say I do the rotation first, so A comes here, and then I do the vertical flip, so A still comes there. So I still get H here. If I do the horizontal flip followed by the rotation, so again tracking where A goes, horizontal flip first, and then rotation goes to here. So that's the same as what would happen if I just did the vertical flip. And that goes the other way too. If I did the rotation first and then did the horizontal flip, so the rotation would bring it here, horizontal flip brings A here. So that's the same as the vertical flip. And then finally, horizontal followed by vertical. Let's again track where A goes here. And then the horizontal flip goes there. Well, so A ended up on the opposite corner. It also ends up on the opposite corner if you do the rotation. So I'll just finish this up. You can try the other way around. So this is the Cayley table for the symmetries of a rectangle. So this table, or this group, has a name, or we say that it's isomorphic to the Klein foregroup. Oftentimes we just call that group K for Klein. And the reason for it, the sort of identifying characteristic here is that every element has order 2. So each symmetry has order 2. What does order mean here? Well, just how many times you have to do it over and over again, or how many times you have to repeat it to get back to the identity. And notice in each case, if we repeat it once, or repeat it twice, essentially, repeat it once, it's hard to say which one of those is correct grammatically, but if you repeat it, you get it back to the identity. So it has order 2. Okay, next let's look at the equilateral triangle. I'll try and put a little bit more detail into the equilateral triangle because it is a little bit more complicated. So first let's draw a picture of an equilateral triangle. And again, we'll label the corners. So we'll start with this labeling. And we'll think about the different things you can do, and then we'll actually show each representation. So first let's think about how many different things we should get. So notice the positions of A, B, and C, we kind of count out as being different. So like if I were to rotate it, A would go to B, B to C. So if I do just one rotation, which I'm going to call that row for rotation, I'm rotating this way again, but this time by 120 degrees instead of 180. So A goes to where B is, so A is here now, B goes to C, C goes to where A was. So that's the new orientation of those points. Now, so let's think about how many possibilities are there. Well, you have 3 options, A, B, or C, that could go there, and then you have 2 options here, and then finally the last one would be forced. So it's 3 factorial or 6 options. So I should have 6 different orientations of the triangle that I should end up with. I could rotate again. So before, if I rotated by 180, if I rotate it again, I get back to the original. But here, clearly, I don't get back to the original if I rotate again. So if I apply row one more time, then A goes to where B is here, B goes to where C was, and C goes to where A was. So it's a different thing than here. But if I do it a third time, then I get back. So I'll maybe draw an arrow back. I get back to here if I do row one more time. So we'd say that row has order 3. Now, of course, this isn't all that I can do. There are flips that I could make, but I'm going to focus on just one flip. We'll do this flip across a vertical line. So notice that keeps B in place, but it switches A and C. I'm going to call that flip tau. So what does the triangle look like after that flip? Well, B stayed in place, but A and C switched places. So that's another orientation I can get. Now tau, of course, is order 2. If I apply tau again, I just get back. So I still have 2 more triangles to come up with here, but I'm not going to get it by repeating rho or repeating tau. So now I want to do combinations of them, which is what I had up here, but the combinations just gave us one of the other ones, so it wasn't very interesting. So here, again, I can think about the other flips, but we're going to get the other flips by doing these in different orders. So if I do rho first and then I do tau, so I can think of the triangles on this side as doing tau second. So tau again is this vertical flip. So A stays in place, and C and B switch places. So I get B, C. So comparing it to the original, that would be the flip through this line, right? Because A and B switch places from the original, C stayed in the same spot. So I want to give this a name, like going from here to here directly. I'm not going to give it a new name because I can see that it's just doing tau first, or doing rho first and then tau. So I'm going to call this tau rho. Why do I write it in that order? For some reason, we think of this as moving from right to left. So I apply rho first and then tau. I suppose it's the same as how we do functions, right? Like if I say f of g of x, I do x into g first and then into f. So that's the reason why we do from right to left. So I think of this as like applying this to a triangle. I put that triangle through rho first and then I put it through tau. Okay, well, let's keep the whole picture up. The last thing I could do is I could do this rho twice. That gave me something different, and then do the flip. What do I get this time? So I'm flipping this again. Tau is always the vertical flip. So we're going to go this way. So C stays in place, but B and A switch places. Once again, let's compare that to what would happen from the original. So from here to here, A is staying in the same spot, but B and C flipped. So that's actually the flip through that line. So we are seeing all those other flips, but just combinations of tau and rho. And so that was tau twice followed by rho. So I'll call that tau rho squared. And that gives us our 6 triangles. So let's give names to each one. So of course the original triangle is, applying the identity to it would just give you that. This is what I get by applying rho once, and this one I apply rho twice, so I'll call that rho squared. This one I get by applying tau, and then tau p and tau p squared, so I'll just put those on top. So I can think of these as the 6 symmetries of the equilateral triangle. So now let's create the Cayley table. So just like before, when I did the rectangle, I'll have all 6 of them across the top and down. So I have the identity, I have rho, and rho squared, and then I have tau, tau rho, and tau rho squared. I'll put those here as well. No, I put it in this way because we'll get what we refer to as a subgroup here. If I don't use any of the taus, then these just kind of cycle through each other. So the identity, I'll go ahead and do the identity with everything. Obviously the identity followed by any operation is just that operation. Okay, but I'm going to sort of separate this into 3 by 3 chunks. So if I, again, doing these guys first and these guys second, this is going to make a difference this time. So if I do row followed by row, well, that's row, row, so that's just row squared. If I do row squared followed by row, so do row twice and then row again, we saw that comes back to the identity. Same thing here, that's just row followed by row squared, so row, row squared, bringing me back to the identity. And then row squared twice, so 2 rows and then 2 rows again, just brings me back to row. So notice this little sub box here, sub-Cayley table, doesn't have any taus involved, so it's just a little subgroup inside of the full group. So I could just do only rotations and everything's nice and closed. Okay, so let's focus on this side now. So here, this is doing a rotation first, followed by one of the flips. So if I do row followed by tau, actually, maybe we should do it, oh yeah, that's fine. Row followed by tau is this one, right? So that's just tau row. And then we could do this one too. That's the natural one here too. Row followed by tau squared is, or sorry, row squared followed by tau is this one. Okay. Now let's look at row followed by row tau. So notice, like, what goes in this box is row first, and then row tau. Well, that's row twice, and then tau, again, reading from right to left. So that is, of course, tau row squared. So this corner will actually be pretty easy because, you know, I'm doing this first and then doing this one, so these two will combine. So like this with this is row 3 times and then tau. So that's just tau, because the row 3 times brings us back to the identity, and then I do tau, so it's just giving me tau. These two, same idea. Row is going to happen 3 times first, and then tau. That's just the same as just doing tau. And the final one, row 4 times, followed by tau. Well, that's like doing row once, and then tau, so that's tau row. Now this corner might be a little bit trickier, because we're going to do something involving tau first, and then things involving row. So tau followed by row. Let's sort of imagine this one. So tau first, and then row rotates. So if I were to rotate here, B ends up here, A ends up here. So it looks like it goes here if I were to do a row. Is that right? No. B goes here, and A goes here. So it actually goes to that one. Well, that's the same as tau row squared. Sorry about that. So tau followed by row is actually tau row squared. So let's notice something here right now. So tau row and row tau gave me different things. So let's notice that this is different from this one. So row followed by tau was tau row, this one here. And then tau followed by row was this one. So this is our first example of a group that's not commutative. So I can do operations in different orders and get completely different things. Now I don't want to spend too much time here, so let's just fill in the table. I'll let you, you can pause the video and try and fill it in on your own, but I'll fill it in just to have the full table here. can talk a little bit more about the last corner here in a second. Notice the identity hasn't popped up too very often just yet. We've had 3 identities here. So this is where we'll see more of them, because any flip with itself, so tau and tau will give me the identity, but tau rho with tau rho should also give me the identity, because that's this flip. And then tau rho squared with itself should also give me the identity. So I get a couple identities there. And it actually turns out that any of these flips with another flip, so tau with tau rho, or tau rho squared with tau rho, should give me one of the rotations. So what you end up with is these rotations. Okay. So that's the full Cayley table for the symmetries of the equilateral triangle. So again, notice, well, this one was commutative, and you can tell that it's commutative if it is symmetric about this line. But here it wasn't. Like you can see many places, like tau rho with rho squared gave you this one versus this one, so those weren't the same as each other. So it's very much not commutative. You have portions that are, of course. If you just have rho and don't include tau, then those things will commute with each other. But tau and rho don't commute. So we usually call this one D3. In general, we'll have an n here for an n-sided object, for 3 for a 3-sided object. So 3 is just the equilateral triangle, but we'll look at D4 later, which will be the symmetries of a square. So these are your regular polygons. And we can say that this is the set, of course. So the identity, rho squared, tau rho squared. Oops, I forgot tau in there. Tau. So it has 6 different symmetries. But notice that everything in here is just combinations of tau and rho. So I could say it's generated by. So whenever I use angle brackets like that, I'm saying that I'm generating all combinations of the following things. So it's generated by rho and tau with particular relationships, namely that rho cubed is the identity, tau squared is the identity. So these are all the identity, and how they interact with each other. So tau rho is the same as rho squared with tau. So those are sort of the defining properties, or tells you how they interact with each other. So if you make any combination of taus and rhos, you should be able to sort of simplify them down to one of these 6. This is also called S3, as it turns out. It's equivalent to, or isomorphic to, just all the permutations of 3 numbers, or 3 objects. Okay, I thought maybe I'd have enough time to start the next section, but I think we'll stop this video here and then start the next video on 3.3, where we'll finally give the definition of a group. So far, we've just been looking at a few examples of groups. So we've seen so far Zn, so the integers modulo n, and we've seen the Klein 4 group K, and we've seen D3, which is isomorphic to S3. So those are the groups we've seen so far, but of course we'll see many others.